So here's a thing that made me sit up straight this week. For years, the story about advanced chips was basically one sentence. Only one company on Earth can build the machine that makes them, and that company is ASML in the Netherlands. That was the whole game. Full stop. And now, there are credible reports that China has actually built a working prototype of a machine that does the exact same job, sitting in a lab in Shenzhen. If that's true, and I'll be careful with that world all the way through this, then one of the biggest technological choke points in modern history just cracked. Stick with me, because I'm going to walk you through how they pulled it off, what's real, what's hype, and why this matters even if the machine is nowhere near as good as ASML's. And do me a favor before we dive in, hit the subscribe button, because I go deep on this chip war stuff every week, and it only gets more insane from here. Alright? Let's get into it. Let me introduce you to the deal, because you can't understand why this is a big one until you know what these machines do. Advanced chips are built by shining light onto silicon and printing circuits smaller than a virus. To get features that tiny, you need extreme ultraviolet light, EUV for short, at a wavelength of 13.5 nanometers. Regular light is way too fat and clumsy to draw circuits that small, and here's the catch that makes this field so brutal. Nobody could reliably produce usable UV light at industrial scale except ASML, and it took them 2 decades and billions of dollars to get there. The way ASML does it is honestly a little insane when you say it out loud. Inside their machine, a system fires around 50,000 tiny droplets of molten tin every single second. Each droplet gets zapped by a powerful CO2 laser. Actually gets hit twice, and that turns the tin into a superheated plasma that spits out EUV light. That method is called laser-produced plasma, or LPP. It works, it's proven, and TSMC and Samsung use it to make basically every cutting-edge chip in your phone and your laptop. This is the crown jewel, and it's the exact thing the United States and its allies have blocked China from buying since 2019. No EUV machines for you. That was the policy. Now, here's where it gets spicy. In December 2025, Reuters dropped an exclusive report saying a team in Shenzhen had completed a functional EUV prototype earlier that year, now undergoing testing. And the detail everyone latched onto, myself included, is who reportedly built it. According to Reuters sources, the machine was developed by former ASML engineers who reverse engineer the company's EUV systems. People inside China are apparently calling this a Manhattan Project, a whole-of-nation effort coordinated with Huawei at the center, pulling in thousands of engineers across companies and state research institutes. And the cloak and dagger stuff is wild. The reporting says the secret lab was so paranoid about foreign spies that employees were given fake IDs. That talent grab kicked off around 2019, offering signing bonuses of 3 to 5 million yuan, which is roughly $400,000 to $700,000, plus housing subsidies. One big name is Alina Nunn, ASML's former head of light source technology, whose team at the Shanghai Institute of Optics reportedly filed a stack of critical EUV patents in about 18 months. You cut off the machines, so China hired the people who built them. From a pure strategy standpoint, you kinda have to respect the move. Now, here's a physical detail I love. ASML's EUV machines are famously compact, roughly the size of a bus, engineered to fit neatly onto a fab floor. The Chinese prototype does the opposite. It reportedly fills an entire factory floor, and that's not a bug. That's the whole strategy.
So ASML uses that tin droplet and laser method, LPP. China is chasing that too, but the prototype getting all the attention uses a different approach called laser inducted discharge plasma, or LDP. Instead of firing lasers at falling droplets, LDP vaporizes tin between two electrodes, often described as rotating tin-coated discs, and then slams it with a high-voltage electrical discharge that converts the tin cloud into plasma. That plasma spits out the same 13.5 nanometer UV light, which means the same wavelength, just a different path to get there. Why go this route? Because LDP is mechanically simpler. Fewer of the insanely complex laser control systems, a more compact light source, lower energy consumption, and, crucially, it dodges a huge pile of ASML's restricted patents. That's the strategic genius of it. If you can't legally copy the LPP path, you build a different door into the same room. The catch, and it's a big one, is that LDP has historically struggled to deliver enough raw power for high volume manufacturing. Okay, the light source is only half the battle. Let me tell you about the two things that keep semiconductor engineers up at night. First, the optics. At EUV wavelengths, light doesn't pass through lenses. It gets absorbed by basically everything, including glass. So you can't use lenses at all. Instead, you need mirrors. Ultra-precise ones coated with dozens of alternating layers of molybdenum and silicon, polished so smoothly that if you scaled one up to the size of a country, the biggest bump would be a few millimeters. Traditionally, only Zeiss in Germany could make these. That's the other half of ASML's secret sauce, and here's what surprised me. China's Changchun Institute of Optics, CIOMP for short, reportedly built its own molybdenum silicon multi-layer mirrors, hitting around 65% reflectivity. Now, Zeiss glass mirrors sit closer to 70%, and that gap sounds tiny, 5 percentage points, but here's the brutal math. An UV machine bounces light off 10 to 12 mirrors in a row, so that small loss compounds at every single bounce, and by the end you've lost a huge chunk of your light. China's answer is to compensate by making components bigger and accepting lower efficiency. Cruder, sure, but it points photons at the wafer, and right now that's what counts. Second problem, and this one is sneaky, helium. EUV manufacturing runs on it. You need helium for cooling, for its non-reactivity so it doesn't mess with the process, and for leak detection, and there's basically no practical substitute. China imports most of its helium. So, in an interesting twist, China has moved to restrict helium exports to prioritize its own domestic fabs. The Chinese prototype's light source reportedly puts out around 100 watts, with some reports stretching that to 150. Sounds fine until you compare it. ASML hit 250 watts back in 2017 to churn out 125 wafers an hour. Their current systems run around 600 watts, and they've been talking about a 1,000-watt system in early 2026 research. High-volume manufacturing really wants at least 250 watts, so China's prototype is running at maybe a third to a half of the entry-level bar, and its throughput is reportedly around 10 wafers per hour. Slow. But, and this is the part I really want you to hear, it doesn't have to match ASML to matter. Not even close. Right now, to make advanced chips without EUV, Chinese fabs like SMIC learn on multi-patterning with older DUV machines. You run the wafer through over and over, layering patterns to fake the resolution EUV gives you in one shot. It works, it's slow, it's expensive, and it wrecks your yield because every extra pass is another chance for something to go wrong, but it works, so think about it. Even a limited, clunky, factory floor-sized EUV machine that beats that multi-patterning grind on the most critical layers would be a massive strategic win. You don't need to beat ASML. You just need to beat your own worst workaround. So, let me give you my honest take. Is this real? The light source and the physics appear to be real. Reuters says that the machine is in operational condition and is generating EUV light, though it has not yet produced working chips. And there's a real caveat there because the prototype was partially assembled using salvaged parts from older ASML machines and components from Nikon and Canon. So, it's not fully homegrown yet. ASML's own CEO said back in April that China would need many years to develop this technology, and he might still be right about the timeline for a competitive product. Turning a prototype into a reliable, high-volume production is a multi-year slog through yield problems, photoresist chemistry, and metrology, the boring-sounding stuff that decides whether a fab makes money. But here's where I land, and I'll be straight with you. I find this really impressive. Everyone assumed that EUV wall was unclimbable, that it would take China a decade or more if it happened at all. And instead, through a mix of poached expertise, a clever workaround technology, homegrown optics, and relentless national willpower, they've got light coming out of a machine years ahead of what most experts predicted. That's not a full victory. The game over is a headline and not a fact yet, but it is a genuine crack in a wall people said was solid. And in this industry, cracks have a way of widening fast. My bet is that the next signpost to watch isn't the prototype. It's whether they push that light source towards 250 watts without cooking half their energy into waste heat. That's the moment lab toys become factory tools, and that's the story. One of the most fascinating chapters in this whole chip war, so if you found this useful, smash that like button because it helps the channel more than you think, and subscribe so you don't miss where this goes next. Trust me, this saga is far from over. I'll see you in the next one.